as we discussed in the previous video, we're just going to take one part of it for the solution. Let's say I'm taking x1 of t. My x1 of t would be, if I'm splitting this into 2, I'll get e to the minus half t and e to the it times 1 and I, right? According to Euler's formula, we have e raised to the power it as cosine t plus I times sine of t, right? I'm going to bring this into our answer. We're going to split it into 2. So my x1 of t vector is going to be e to the minus half t times cosine t plus I times sine of t times 1I, right? So now I'm going to just split this into 2 parts where I'm bringing all the real components on one side and all the imaginary components on the other side. So that would make it e raised to the power minus half t times cosine t, right? And at the bottom, my I and I would be giving me a -1. So for the real component, I'll be taking this multiplied with this, right? So that would make it I squared is -1, so I'll have a negative symbol. And I have this one, so I'm going to have e raised to the power minus t over 2. And then it's the sine component of it. Okay. Then plus, now if I'm taking the imaginary components, I would have e raised to the power minus t over 2. And then in the first row or the top row, like I has to be multiplied by 1 to give me imaginary. So I'm going to have sine in the numerator, in the top row. And in the bottom row, I'll be having cos, because cos multiplied by imaginary is the one that's going to give me e raised to the power minus t over 2 of cosine t, right? Okay, since I squared is equal to -1, which is a constant, right? Since I squared is a constant, I should also be a constant for us. Using that concept, we're just going to say that this is still a linear combination of 2 vectors. And we'll say that this one would satisfy the differential equation that is stated there. My final solution for the differential equation can just be only this one. Because when you think about it, if I do this one, I'll still be ending up with a similar answer. So I can start off with x2 of t or x1 of t, and that does not matter. It should not matter. Okay? We have split it into the real and imaginary components. But we still have a doubt because we have taken only one of the part of solution, right? Which is like only one eigenvalue and one eigenvector. So if you remember from the previous series of videos, we did something called the Wronskian to check if my solution is going to be independent or not. So I'm still going to do that over here. So I'm going to take the Wronskian, right? But for which two will I take? That's the question now. Since we are writing this as a linear combination of 2, so I'm just going to take this vector as one of them. We say that since I've already used up x1 and x2, let me just say xm and this one as xn. Okay, these are something else. Okay, it has nothing to do with x1 and x2. So if I do the Wronskian of xm and xn vector, honestly I should have just used some other name other than x. Okay, I would get the determinant of e to the minus t over 2 cos t minus e to the minus t over 2 sine t, e to the minus t over 2 sine t, and e to the minus t over 2 cosine of t. I get this determinant, right? Let's see what the determinant comes out to be. So if I'm multiplying the exponentials, so it'll be e to the minus t over 2 squared, we'll just make it e to the minus t times, I'll have a cosine squared t, right? Then minus, when I do this, I'm again going to have e raised to the power minus t, because e to the minus t over 2 squared would make it e to the minus t. and this negative would be absorbed by the negative in the determinant, so that'll give me plus. Then sine t multiplied by sine t would make it sine squared t. And we know that cos square t plus sine square t is 1, so this is just e to the minus t, which is not equal to 0. Right? Since our Wronskian is not equal to 0, we can say that this is a unique solution. And hence we can write our final answer, final solution to the differential equation as using the constants now. C1 times e to the minus t over 2 times cosine t minus sine t plus, okay, now I is another constant, so I'm just absorbing the I to my new constant, which is C2 times e to the minus t over 2 times sine t and cosine t. Okay, so now I've again made it as the linear combination of the two solutions. This is how we approach it. So if you look at it, we are having a real component and also a complex part in our solution. We have to graph it only in the polar coordinates. So when it comes to polar coordinates, everything is going to be circular. That is what explains the spiral and the concentric shape of the complex eigenvalues, which is different from the real ones. This is the final answer. You can just pause it for a minute and take a look at the solution. Thanks for watching.